네, 그러면 today we're gonna study about deep reinforcement, deep learning from linear regression. Okay. So first of all, I would like to let you know what is the linear regression at first. Okay. So first of all, we're gonna study about what is the linear regression. So linear regression. So in supervised learning, I told you that we have two types of the technique that is called linear regression and classification. So we're gonna study about the topics one by one. So for linear regression, so we can think about the exam score prediction. So that is kinds of the estimation of the tendency of data distributions. That's why that is very useful in many applications. So suppose that we have three samples, as you can see right hand side. So x comma y will be 1 comma 10, 2 comma 15, 3 comma 40. That means that we have three samples just like that. You can also interpret these kinds of results as follows. So suppose that we have three students. The first student studied only 1 hour and the students take 10 points. The second student studied only 2 hours and he or she took 15 points. And last student studied 3 hours and he or she took 40 points. So then you can see the results just like that. So we have to estimate the tendency of the score, and also we have to estimate the relationship between the studying hour and the results. Then we have to make a model or estimation. So in this case, we have to study about linear regression. That's why our model is linear. That's why, as you can see over there, linear model, h of x, the function is wx plus b, because we have to represent as a linear function. That's why there should be ax plus b linear equations. So here, the model is called h of x because in statistics, that is called hypothesis. That's why we usually use the notation of capital H in order to represent the model. And then the angular value is capital W, which means that the reason why we are using capital W is that the W is the weight, means weight, and that is used in neural network weight. So eventually this model will be translated or evolved to neural network architecture that can be represented as weight as a neural network model. That's why we use W here instead of A, and then we use it as capital because we can have multiple number of WX. That's why they can be vectors. So the among given three linear curve, red, blue, yellow, which one is the best? So you can think that blue might be the best because it has a small difference between samples. So we are saying that the blue is the best. That is our hypothesis or our linear model. That's why we can denote that as h over x. So as you can see, the function. So we want to make the line is very similar to the samples. That's why the gap between the sample and model should be very small. That's why our main objective is minimize the gap between the curve and the plot, curve and the dot sample. That's why our cost function that should be minimized can be represented as follows. So in each x values, it has its corresponding the actual observed data, sample data, and then we have linear model. So we have to see the gap between them, and we have to minimize the gap. That's why we have to subtract the value from the other, and then we have to take the square because we do not need a sign notation anymore. We just see the gap, or we just see how much they are difference. That's why the sign has no meaning at all. That's why we have square, and then we are taking the average of the all given samples. That is the main equation for the cost function. That is called cost function because when you have more and more gaps between sample and estimation, then we have more and more errors. That's why that should be the cost. That's why we are saying that there is the cost function. Otherwise, they can be also called as loss function because we are losing the accuracy. Okay, so that is called cost function. So here, x and y are not variables. So you have to keep in mind this one. Okay, x and y are not variables. X and y is just a sample constant given values. our variables are W and B because we have to find the W and B in order to identify the linear model. That's why, as you can see in cost function, our variables are W and B, not X and Y, okay? So this is the end. This is very simple, right? So our main objective is cost function minimization. We have to minimize the cost, then we have to minimize the gap between the sample and the estimation, and then it means that our estimation, which means our linear model, is very similar to sample, then that should maximize the accuracy. That's why our main objective is cost function minimization. So for that purpose, we have to set up our model, linear model, h of x, that is defined as wx plus be, and then our cost function is taking the difference between the model and the sample, and then we take the square in order to eliminate the sign, and then we will take the average, okay? So then we can see the result just like that. So in this case, we are saying that this is a mean square error. So mean square error, MSE, is just like this cost function, okay? This cost function is also called mean square error. So our main objective is minimize this cost function. So for that purpose, we are using gradient descent method. So gradient descent method works just like that. We will starting with one random point. At the random point, we will take the angular value, and the angular value is very big. It means that there is gradient. If the gradient is very big, it means that we are far from the optimal point. That's why we have to jump a lot. So that's why the arrow is very long. But the point becomes the point approaches to the optimal point, then the angular value or the gradient becomes smaller and smaller. It reaches to 0, then we are converging to the optimal solution. That's why we can denote the notation as you can see in the left-hand side. In left-hand side, we have W value, that is our value we have to find because that is the angular value. So then we are taking the partial differential for our given cost function because we are taking the angular value. We have to look at the angular value. If that is big, then we have to change the W value a lot. If that is very small, near 0, then we are converging to the current value. That's why we can make a notation just like that, as you can see left below. But you can see alpha also in the equation. So alpha means learning rate. If that is big, then we have to jump a lot. If that is small, we jump small. So then if alpha is too large, then we are doing the overshooting because that is very low. And if that is very small, then our jump is very small. That's why it takes a lot of time to converse. That's why we may stop in the middle. That's why learning rate control is very important, but it depends on the sample data. If the sample data has a lot of, consists of very big values, then we have to set the learning rate very big. If the sample data has very small numbers, consists of small numbers, then the learning rate should be small as well. That's why it depends on the given sample training data. That's why we cannot have any kinds of mathematical framework for this one. We have to find the value by trial and error. That's why it takes some time. That is also called hyperparameter tuning. Okay. So in addition to that, these kinds of gradient descent method cannot be used for the non-convex functions. So if our given function is convex, then we can use gradient descent. Otherwise, if our function is not convex, as you can see in this illustration, we may converge to local minimum. That's why gradient descent method is always available when our cost function is convex. Okay. So in addition to that, up to now we consider only one single x value, but we can consider more and more x values. So as you can, that is called multivariate linear regression. So as you can see in our model, in this equation, we have n different x values, n dimensional x vectors, and then we have w values for individual x's. That's why we have n number of x values, n number of w values, and lastly we have one bias plus b. So then, even though we have this kind of situation, the cost function design is similar to what we did with one variable linear regression. So we have to observe the sample at first, and the value is y super I, and then based on that, based on the given n number of x values, we can make a linear model. The model will return one estimation. The estimation should be very similar to our sample data. That's why we have to take the minus between them, and we can see the difference between them, and then we take the square, and then we have to minimize the gap. Then our estimation result should be similar to our sample. Then the basic concept is still similar to the case where we have only one variable, even though we have multiple variables. But programming with multiple variable is not easy, because maybe the number of x will be 1,000, 10,000, or 100,000, and so forth. That's why doing the programming in that way is not difficult, it's not easy at all. That's why we can make a vector for each w and x. So as you can see in the white box, we have 1 by n x vector, we have n by 1 w vector. When we are doing the multiplication, then we can make the linear combination at one time. That's why usually when you are doing the programming, we make a vector for x, we make a vector for w, and then we are doing the matrix multiplication. Then we can easily program the linear model with this technique, okay? So this is all theory what we have. So from now on, I want to show you how you can do the programming for the linear regression, okay? So first of all, I will let you know how to do the programming with the TensorFlow, and then we have Keras. But Keras, so Keras is a library for neural network or deep learning, and Keras is purely for the deep learning. So in this case, you have to understand the basic terminologies in neural network and deep learning. That's why studying about Keras can be done once you understand the neural network architecture. That's why let me do this way. We will gonna study about only TensorFlow until we study about neural network. So once we study about neural network, we will go back one by one. Then we will see how the Keras is organized. Okay. So at this time, we will gonna study about what is the TensorFlow only. So this is the one basic architecture for TensorFlow. So we in our linear regression. So please look at the right-hand side upper illustration. When the x is 1, 1, it means that our data is 1, 1, then the result is 10. If our input is 2, 2, then the result is 20. If our input is 3, 3, then the result is 30. That's the linear regression model, and that's our given sample data. Okay, we have to do the train this one, and then since we have two x values, we have to find two w values for individual x values, and then we have to find b. So we have to find three values from this code, okay? In line first, we have TensorFlow definition. Line 3, we have x underbar data. Line 4, we have y underbar data. So within there, we have to set our training data. So in x underbar data, we have 1, 1, 2, 2, and 3, 3. In y underbar data, we have corresponding results. Those are 10, 20, and 30. It's line 5. So we have to make a placeholder because we have to put a lot of data inside there. So in my programming style for the placeholder, that placeholder means that we will take the value directly. We have no calculation yet. That's why I set always the placeholder as capital. So in line 5, our x is capital. Line 6, there is also return value of placeholder. That's why there is also capital. So line 5 and 6, our x and y values are capital. Okay. So in x, we have placeholder, though the values are floating, and the shape is none, 2. None means that we can have multiple values, and 2 means that we have two values for individual input sample. So for individual input sample, we have 1, 1, 2, 2, 3, 3. That's why we have two values. That's why in shape, we have none, 2 in line 5. So in line 6, that is for y. Y is placeholder and float 32, and the shape is none, 1. None means that we can have multiple values, and 1 means that we have only one value. So as you can see in line 4 in y underbar data, our data are 10, 20, 30. That's why every single input we have one data. That's why that should be 1 as well. So x looks like 1 by 2. Okay, that is 1 by 2 matrix. That's why in order to do the linear combination, matrix multiplication, W should be defined as 2 by 1. That's why when you define W as variable in line A, W is TF dot variable, and that is TF dot random underbar normal and 2, 1. The reason why you have 2, 1 is that W should be defined as 2 by 1 in order to do the matrix multiplication with the x, where the x is defined as 1 by 2. And then that is inside the function of random underbar normal, which means that we're gonna start with the random value. Those are taken from normal distribution, Gaussian normal distribution, okay? B is also one value, and that's why we are defining it as tf dot variable, and then there is tf dot random normal, and we have one inside there. It means that we will take only one B value, and that should be random normal. That's why there is one in one value, that's why it's one. So in line 11, 12, 13, we are in line 11 we are making model. Line 12 we are defining cost. Line 13 we are making the train. So these three lines are major component or the key component in this TensorFlow code. So in line 11, so we are doing the linear combination at first. That's why we have x comma w inside the tf dot matrix multiplication and plus b. Plus b means our bias. And then we set up our model. So in cost function we have to check the difference between the model and our real value. That's why real value is y, because y is placeholder. That's why y will take the real value directly from the memory. That's why we will gonna measure the difference between model and y, and we will take the scale in order to eliminate the sign, and we will gonna do the average. That's why for the average we are using tf dot reduce underbar mean function in line 12. That's why in cost function we are taking the difference between model and real numbers, real values, and then we are taking the scale, and then we are taking the average. So that definition is exactly the same what we studied before. And line 13, we have to start the training. So in that case, we have to implement gradient descent optimizer. So in this case, TensorFlow provides one function that's called tf.train.gradient descent optimizer. And then our objective is minimize the cost function. That's why we have that minimize cost, and our learning rate is defined as 0.01. So by typing these three lines, we can simply implement the linear regression with TensorFlow in Python. Okay. Once we set up all model, cost, and train, then we will gonna start the session in order to the calculation. Okay. So once we call line 13 by calling the variable train, we execute only one optimizer. So here, when you look at this one, this one arrow is one optimizer. So once we call this one multiple times, we are converging to the optimal point. So the line in the code, if we call this one 2,000 times, then we're gonna jump 2,000 times, okay? So this is only one jump, one jump, one jump, and so forth when we call the train function, a train variable. So here, so within the session, in line 15, in line 16, we are initializing all the global variables by calling a tf.global variables initializer. And then from line 18, we are starting the training, okay? So we have for loop, we have step from 0 to 2001. And then while we are executing the iteration, so within there, for function, we have session run in line 19. Session run means that we will execute the session. So as you can see in line 8, 9, 11, 12, 13, WB model cost train variables are all tensor type because they are the return values of the TF functions. That's why in order to execute or in order to get the real values of the variables, we have to make the session and we have to get them by typing session.run. So within session.run, we are calling all the four variables, cost, WB, and train. The return value of cost will be stored in small c. The return value of capital W will be stored in W underbar in line 19. The return value of B will be stored in B underbar. The return value of train is not existing because it just make only one jump. As you can see that train is the tf.train.gradient descent optimizer. That's why this one is just underbar, okay? But for this calculation, we need cost. Cost need capital X, capital Y. That's why we need capital Y data. So capital Y should have Y underbar data. That's why Y underbar data is here, and the data will be stored in Y. And here we have model, and model has X. That's why X should have some data as well. So X underbar data should be here as well. Then we will put X underbar data into capital X, Y underbar data into capital Y, and then we can make the training. And then we will print out 2001 time. Once we are done in line 21st, we are all done for the training, okay? Then we can iteratively find WMB here. So here in line 21, once we are done for the for loop, we calculate WMB values. So we have WMB values. That's why in this model function, we find WMB. That's why when we have X, we can estimate the result. That's why in X we put 4 by 4. So when we have 4 by 4, then what will be here? Maybe 40. So we can see that 40 is derived by this code 1 in the next slide page. So once we are done for the iteration 2000 times, we will get the result, and we can see that the result is 39.989, which means that that is near 40. That's why the training is very nice here. So we can check that in this code, okay? So next we're gonna see the keras, but as I told you before, keras will be studied once we understand neural network. That's why that code will be studied later, not this time. So here's the end of the linear regression. For the next time, we're gonna see what's the binary classification.